All right, as on me, I guess. Hello. Thank you all for coming. This is the third installment in the UMass Cybersecurity Club's series of workshops on Capture the Flag. And tonight we're going to be talking about the software reverse engineering category. And first, I think very few of you know who I am. I'm not a current student here. I'm a UMass alum, working for the Department of Defense full-time. I graduated last year. And I really like reverse engineering, but I also hate talking about myself, so let's get into the presentation. So we're going to start off with a kind of high-level overview of software reverse engineering, kind of go into the background that's common among software reverse engineers, describe what it is, and that is going to involve talking about assembly language. If you don't know about it, don't worry, because we're going to talk about that. And then we're going to start to learn our tools, which are going to be NSA's Ghidra software reverse engineering suite and the GNU debugger. And then finally, because this is a workshop, we're going to have a hands-on component where we are going to reverse engineer a little program that I wrote. So yeah, we'll talk about reverse engineering. Leading with a question like this is a little bit hackneyed at this point, but what is software reverse engineering and why would you care? So like other uses of the term reverse engineering, the idea is that you have some sort of finished product and you're trying to pull it apart to figure out how that works. And that's intentionally a very broad, unspecific definition because what figure out how it works means could depend on your situation. So on one end of the spectrum, you might be interested in a very specific functionality of a program. So one example that you might see in Capture the Flag is the case of a license key for software. Say you want to generate thousands of illegitimate license keys. These kind of challenges are called key gen me's or crack me's. But in this case, you're only interested in the key verification algorithm because you want to develop your own, or not necessarily your own, but you want to develop something that can invert that verification process and generate a key. So a reasonable course of action would be to open up your tools and reverse engineer the installation wizard and figure out how the verification algorithm works, develop your own key generator. On the other end of the spectrum, which is one that you don't see quite as much in Capture the Flag, you might be wanting to develop an entire specification for a piece of software so that you can re-implement it from scratch, build a competitor. In Capture the Flag, kind of the close analogy to this would be the optimize me categories of challenges, where you're given some sort of algorithm which generates the flag very slowly. And the goal is to reverse engineer it to figure out how to develop an algorithm that would be faster so that you can actually generate the flag within the time constraints of the competition. What I have on the slides here, this is kind of a real-world example of software reverse engineering where some people reverse engineered the Intel BIOS, so that's the little chip that's on your motherboard that runs before anything else, and they managed to re-implement the firmware from scratch so that you have like an entirely open source computer. But yeah, reverse engineering or software reverse engineering, how does it differ from real world reverse engineering? Kind of an obvious difference would be that with real world reverse engineering, you have like, hammers and screwdrivers and heat guns, and you can just kind of pull the thing apart. But with software, you can't really do that, right? It's not really tangible. So what are you given anyway? And I mean, at a kind of general description, you're given build artifacts. So maybe an executable.
You're talking very fast. I'm sorry. Maybe it's just because I'm unfamiliar, but I can't really keep up.
Okay.
Just talk slower.
So actually, I should probably address this. Rules of engagement. If at any point you have a question, you can feel free to get my attention, preferably raising your hand. I will be stopping occasionally to make sure everyone's on the same page, but I'd prefer to address misunderstandings sooner rather than later. So actually, that might be a good cue. Any questions at this point about what I've been talking about? Looks like we're good. Okay, I'll try to slow down a little bit. So yes, software, what you're typically given is a build artifact. So this would be the output of some software build process. Some examples that you might be familiar with are like a .exe file in the case of Windows, or maybe you're using your Linux package manager and you're getting an executable. But yes, a file. And maybe you've been curious enough to open such a file in Notepad, and you see that it's kind of gibberish. And what's actually in this file is code, and you might be a little bit confused by that because this doesn't look like it makes any sense, right? The reason is that this isn't code for a human. It's not the kind of Java or C++ that we would write. It's code for the computer, and this is because computers are kind of dumb. They don't understand code in the way that we understand code. They only understand machine code, which is bits and bytes, and each of those strings of bits and bytes describes a single thing that the computer can do. And we'll talk a little bit more about instructions, but that's kind of the explanation of what you're given when you're reverse engineering. You have a build artifact that is explaining code in some sense, but this code is for the computer, and you want to make sense of the code that's for the computer, even though it's not meant for humans. So how do we get this machine code? It's typically when you're reverse engineering a build artifact that you come across in the wild, the machine code wasn't written by a human. It was written by a tool that's called a compiler. So what the compiler does is it takes code in a high-level language such as C++ or Java, and it converts it to machine code. This is a one-way, well, not necessarily one-way transformation, but it's a lossy transformation. So what that means is that you're losing information as you go across this process. However, you do gain some information as well in the form of metadata, and we'll talk about that. So let's just kind of quickly go through this simplification of the process of compilation. So we start with some source code, say in the C language. And if you don't know C, don't worry. The examples I use should still be relatively readable to someone who understands Java. This is the famous Hello World program, just prints Hello World to the terminal. And what the compiler does is it will parse it, and it will compile it into this. And this is assembly language, kind of what I mentioned in the introduction. And this is still, reasonably understandable. I mean, maybe you don't understand what these words mean, but it's not like what we saw in Notepad. So each of the thing with assembly language is it's relatively close correlation to machine code. So each of these lines represents an instruction in machine code, and we'll talk about these instructions soon. But that's the step of that's the role of the compiler. It takes source code and it transforms it into this textual assembly language. And at this point, the assembly language is fed into another compiler, except we don't call it a compiler, we call it an assembler, which converts those lines of human readable text into bits and bytes. So this is what we did see in Notepad, except when you interpret these numbers as text, it comes out all garbled because it's not actually text. Here I'm representing it in hexadecimal. Is everyone familiar with hexadecimal? If not, it's okay. I'll explain it quickly. Everyone knows hexadecimal. Sweet. All right. So yeah, this is kind of the bits and bytes, the machine code. And finally, there's a step called the linker. So the linker takes this machine code and actually turns it into an executable. So machine code, you can't just tell your computer, hey, run it. There's another step involved, which is to say, OK, operating system, I have a program that I want to run. Can you run it for me? And this is the role of an executable file, right? Like when you run a program, you're like double-clicking on the .exe, or you're typing in the name of the executable in your shell. And then the operating system loads that program and runs it. And that's the purpose of the linker stage, is to get it to a format that the operating system understands as a program so that you can run it. And here's kind of a shell session where I'm showing, I'm running the command gcc. That's the GNU C compiler. So, in Linux, the compiler is kind of like all of those steps. It's the step from transformation to assembly, but also turning it into machine code and turning it into an executable. That's represented by that single command. But then I'm also showing file. If you're not familiar with file, this explains, well, it tries to parse the file and tell you what it is. So in this case, it's telling us it's a ELF, so executable and linkable format, ELF. Pretty cool name, I think. But it's telling us that it's an executable. It's written for x86, x64, which we'll talk about shortly, dynamically linked. You can see that there's like a ton of information that we didn't see before, right? Like, this is just like printf, right? There's no dynamically linked, what does that mean? We'll talk about it, but you can see that there's a lot of information in this file despite coming from relatively simple source code. And there are so I told you that it's mostly a one-way transformation. Here's the metadata I was talking about. So we do kind of gain some information, but there's also some information that persists through this compilation process. And you'll see I'm using a tool called Strings, which looks through a file for anything that would be like printable, anything that looks like text. But you can see there's printf, for example. So that came from the source code. We'll talk about why that's in there shortly. We also see hello world. So if you weren't running this file, you might be able to kind of guess what it's doing just from the strings output. And you'll see there's some information that we didn't see, right? There's like hello.c. There's the name of the source code file embedded in this executable. There's also the exact version of GCC that I used to compile this. So yeah, additional metadata. There are what are called symbols. So symbols are essentially human-readable names for parts of the executable. So the executable file is necessarily just going to be a bunch of bytes. It is structured, but it's not text, right? When we tried to open it up in Notepad, it just looked like gibberish. Symbols are something that come through the compiler. They're names for parts of that structured file, the bits and bytes. And a common reason you'll see symbols is because they're typically attached to functions within the file. So if you recall, in our source code, we had this main function. Some of you probably know that main is the first function that gets called when the program's run. But that has a symbol, and it's at 1139 hexadecimal. I think I have the conversion in my notes. But if you open up the file, you start at the beginning, and you walk 1139 hexadecimal steps forward, you'll be at the machine code for main. So the symbols help you to find things in these files. And if you'll recall, kind of the reason we're having to use these tools to reverse engineer is because we're given an executable. We don't really know what's inside of it. We want to go back and kind of figure out the semantics, the purpose, how it's implemented. And these symbols kind of help you because you can see, oh, there's a main function. Maybe I'll look there to see what the program's doing when it starts up. Symbols, they're typically removed from an executable, actually. So this is kind of an unfortunate example because if you're reverse engineering, say, malware or something that you find in the wild, you're probably not going to have symbols. They're removed for reasons of optimization because your file is a lot smaller if you don't include symbols, but you might also just not want people reverse engineering your stuff, so strip off the symbols to say, have fun. But if you're coming across something in the wild and it has symbols, you can use readelf. It'll help you out. It'll make your job a whole lot easier. But there's also, so actually, let me show the correspondence with file. So I just talked about symbols, and I talked about removing them with the strip command. So file will tell you if a executable is stripped or not. That's this part of the information. So this file was not stripped. That's why we could get the symbols. And what I'm going to talk about next is dynamically linked. So is everyone familiar with libraries in the context of programming? Anyone not familiar with it? Yeah. So I'll give kind of a quick explanation. So are you familiar with programming like Java? Okay, so a library would be like those functions that you don't write yourself, but you call anyway. So like system.out.println. You familiar with that? Yeah, so that comes from a library. A library is essentially like any code that you don't write yourself, but you bring in through like import. And there are kind of two ways to implement that with executables. One is static linking, which is when you take the code of the functions that you're using externally and you just put it in the executable. You pretty much copy paste it into the executable. That's static linking. But there's also dynamic linking, which is the executable at runtime will say, these are the library functions that I need, so I'm going to find the library on disk, and I'm going to read these functions into memory so that I can call them. So static linking, it's a little bit harder for reverse engineering if you don't have the symbols. If you have the symbols, it's not too hard, but if you copy all that code in, and then you remove the symbols. You don't have names pointing at the functions anymore. So like, you might spend a couple hours reverse engineering something just to find out that it's like printf. It's never fun when that happens. But dynamic linking is always nice, because in order for the executable to go to that library and say, I want this function, it needs to know the name of the function, right? So the executable is necessarily going to contain the names of the functions that it's calling. So you don't have to, now you're not going to run into that issue where you're like accidentally reverse engineering printf, because you can see this elf needs to call printf, and our tools will actually be able to pick up on those calls to printf. So to kind of summarize, compilation, it's the process of translating computer code written in one programming language. So we use C as an example, but you can think of a lot of languages that get compiled. And the compiler translates this into another language, which is the target language. In the case of our compiler, it's machine code. This is kind of a broad definition, because there are lots of types of compilers. You might not necessarily be compiling to machine code, even though that's kind of what's useful, because you want to be able to run code on your computer. There are cases where you might want to have a different targeted language. And here's kind of another case where you might be reverse engineering something. You have like some JavaScript that gets sent to your browser. You don't know what it does, and it looks like this. This is the output of a compiler. There's a special name for this type of compiler. It's called a minifier or uglifier. So it basically takes like human readable JavaScript and translates it back into JavaScript, except now that you can't read it or make sense of it. But reverse engineering executables, reverse engineering the output of a compiler or build system more generally, is you're given some code, you kind of want to figure out what it is, how the computer is running it, and you want to figure out what tools you would need to manipulate this and understand what it's doing. That's kind of the end goal here. So I'm gonna stop right here. Any questions so far? Good? Sweet. Anything else? Am I talking too fast, by the way, or good speed? All right, wonderful. So we'll move on. Right, so I just said tools. You want tools to be able to interpret the build artifacts that you're being given. In the case of executables that you'd be running on Windows or Linux, .exe or the executable files, you're going to use what's called a disassembler. So if you recall, the step that converts assembly language into machine code is assembly. So going backwards is disassembly, right? It just kind of makes sense. We're going to be using a more sophisticated disassembler, but there is a disassembler on most Linux systems. It's called Obj Dump. And here you can see I'm feeding it this program that we generated earlier, the hello executable. And it's actually spitting out pretty close to what we got out of the compiler, right? This assembly. There's a couple differences, mainly this. This is actually the machine code, but it's spitting out what the corresponding assembly is on the right. So this is what the disassembler does. It goes, so if we go back to this diagram, we go through all of this to get to the executable. The disassembler goes, it reverses the linker, and then it reverses the assembler too to get you to the assembly stage. And now you might be wondering, hey, is there some magical tool that can reverse the compiler, a decompiler? And there actually are. So the kind of caveat here is that compilation is, I kind of described it as one way. I think I also described it as lossy. So you're losing information as you go down the compilation process. You, at the end, have machine code that can be reversed into assembly language reasonably consistently, but the step from source code to assembly is not necessarily one-to-one. So there's a lot of source code that could probably map to the same thing, you can probably think about that. You change the name of a variable, right? Like you can probably create a lot of different programs that compile to the same thing. But you can make a guess, right? Like you can look at the assembly language and kind of guess what the C code would look like based on what it's doing. And that's what a decompiler does. They're not always reliable. Sometimes they're pretty good. Like in this case, it actually managed to figure out almost exactly what the program was. But you can also see that it wasn't perfect. So, for example, I defined it with int argc and char argv. If you're not familiar with C, that's kind of like the equivalent of string bracket args in Java when you have that static void main. Maybe I should stop with the Java analogies, but you can see that that doesn't persist with the main here. I mean, I didn't use it, so to be fair, the decompiler wouldn't be able to figure that out, but that's kind of my point that the decompiler isn't always going to be perfect. However, for our purposes, in the case of our workshop challenge, it'll be sufficient, and you can get pretty far and capture the flag without having to dig into the assembly. The decompiler will be good enough. And I just kind of want to quickly come back to kind of a simplification I made with the compilation to machine code. I kind of discussed it with the JavaScript, where you're compiling to JavaScript instead of machine code, but there are several different execution models, and you might have kind of encountered this in practice. So, you have languages that are compiled to machine code, such as C++, C, Go, Rust. That goes through the general process that I explained earlier. You also have languages that aren't compiled, so like Ruby, maybe JavaScript. That one's a little bit complicated, but you have source code, and you feed it to a program called the interpreter, and it just runs it. So that's a pretty, provided you're not getting the uglified source code, like here, being able to just read the source code and figure out what the program's doing is pretty good, right? So you don't see interpreted a whole lot in the capture the flag reverse engineering realm. But you also have kind of like a meet in the middle. So this one you do see in capture the flag a lot, the VM. So VM stands for virtual machine. You've probably heard of like the Java virtual machine, right? JVM. If not, I'll kind of explain it. So the idea is that instead of writing for machine code for a real computer, now you're writing machine code for like a fake computer. And the reason you'd write for a fake computer is that now you have like kind of a universal platform that's independent of all computers. And something I explain later might enlighten you on why that would be desirable. But point being, it's a different kind of machine code. We call it byte code. But the byte code is interpreted by a virtual machine, like the JVM. A common theme in capture the flag reverse engineering is you implement your own virtual machine, and you write a program that compiles to that byte code. So you're given the virtual machine, and you have to reverse engineer the program. So it's like two steps, right? You have to reverse engineer the virtual machine to figure out how the virtual machine works, and then you have to reverse engineer the program that was written for that virtual machine. Okay, sorry. That was maybe a little bit more in-depth than we needed to go. Any questions so far? Oh, thumbs up. Thumbs up? Okay, cool. It's a little hard to tell if it's a hand raise or a thumbs up. All right, so, yep, that's kind of the caveat. Oh, and then I have a diagram of the JVM. So, we talked about what build artifacts. We talked about how we get to them. Now, there's kind of like two routes in general that you can go for analyzing a build artifact. So one is static analysis, which is kind of what I've been hinting at this whole time, which is parsing the compiled code and presenting it in a format that's readable to the analyst. So you probably recall the disassembler. So that takes the executable and outputs assembly language, which if you're familiar with assembly language might be readable to your likings. But there's also decompilers, which output it to C, which is maybe a little bit more readable. I also have like beautifier in this list. That's the inverse of the minifier that I showed with the JavaScript. But there's also dynamic analysis, which I didn't really talk about. But this is when you're actually running the program to figure out what it does. So our case of the hello world is kind of boring, right? Because all it does is print out hello world. You can just run the program and figure out what it's doing. But you might have something more complicated where you want to open it up in what's called a debugger. So the debugger lets you pause the program and inspect its state as it's going along. And we'll talk a little bit more about debuggers later. But the general idea behind dynamic analysis is that instead of just reading the code, now you're actually running it to figure out how it works. So there's also some methods which combine both. I'll be briefly touching upon them, but they kind of blur the line between static and dynamic. So I kind of think that, let me step back a second. So I just said that the decompiler is typically good enough, but I'm going to be kind of briefly introducing assembly in this workshop. You probably won't need it for the challenge, but I think it's good to know what the computer is doing at the core if you're going to get into software reverse engineering. And it is a little bit important for understanding the dynamic analysis part. And I think that a really good way to learn assembly, if you know how to program C or Java, is to just write programs in C or Java and disassemble them. And there's a pretty good tool here called Compiler Explorer. If you go to godbolt.org, you can get to this. But what it does is you can write source code in any language on the left. It's selected to C++, but it has a huge variety of languages that you can choose from. And on the right, it shows the disassembly. You can also choose a compiler if you want to see differences between compilers. But you edit the source code in real time, and the disassembly updates on the right. So you can see the changes, or see what a change in the source code would look like in assembly. I think it's a cool tool. I think it's incredibly useful. Another thing that would be useful if you're trying to learn assembly is the Intel manuals. They're free. You can just go on Google and search Intel x86 manual. x86, I'll explain in a second what that means. But yeah, the manuals are pretty good. They're super dense, but you can kind of look up instructions. So I'll get into what an instruction is, but you can look up like push and figure out what it does. And yeah, assembly, it's hard to write, but at the core, it's pretty simple. So the idea is assembly has instructions. Your computer, all right, this is a bit of a simplification, but your computer runs one instruction at a time, and it runs them more or less sequentially, unless you have some sort of control flow changing that. And these instructions are loaded into memory, so your computer is running instructions from memory. And the processor has a register, the instruction pointer, which points to a place in memory. And it keeps on moving to the next instruction. So I just said that it's mostly moving sequentially. However, you do have instructions that can alter control flow, and we'll get into that. That's how you implement loops and if statements. But the idea is you have like a little finger pointing into memory. So actually, let me explain memory first. Memory, the kind of analogy I like is that it's a bunch of lockers or mailboxes. So each mailbox or locker is like an address in memory, right? Like a mailbox has an address. You need to have the right address to get your mail. So not my best analogy. Another better analogy would be like the array, right? Like you create an array in Java or C, and it's like 256 bytes long, or chars or ints, right? And each of those ints has a specific number associated with it, right? So like there's the first int in the array, there's the second, and the way you get the first is you index 0 or 1 if you're in like Lua or something. The way you get the second is you index 1, right? So there's a bit of a correspondence between memory and like arrays. So memory, if you're going to think about it as an array, the address is the index. So memory is this huge chunk of bytes, so 8 bits if you're not being super pedantic, and you can treat it as an array. You index into it with an address. And I have kind of a diagram here where we have incrementing addresses, and the memory is all zeros right now. So I'm going to throw you into the deep end here. Don't worry about the assembly. What we're doing is we're going to write a big number to memory. Actually, before I do that, any questions on memory so far? Do you buy me that it's just this big chunk of like bytes that you can address into with an address / index? Nothing? All right, cool. So yeah, we've got the set of addresses which are kind of assigned values. You can think of this as the bytes in memory. And what we're going to do is we're going to write a value into memory, a number, because you can, I mean, do you all buy that you can represent a number as bytes? No objections? Sweet. So we're going to write this number into, I don't know, 4, the address 4. So it's 0, and then we do a write to memory. We're going to kind of explain this shortly. But you see that memory changes. But the thing is, memory, each address stores a byte, but you might have a number that's bigger than a byte, right? So we have to kind of like spread that across multiple indices in the array. Does anyone notice something weird? Actually, might be a little bit more obvious if I give you the hexadecimal version of this number. But you see it was written like this. Does anyone notice something weird? Yeah. Yeah, I mean, little endian, that's what I was going to get into. I was kind of hoping someone would say that's reversed. But yeah, so what you expect is this. But yeah, it's little endian. And a little fact, I guess, that's kind of interesting in terms of reverse engineering or computer architecture. There's endianness, which is when you have a number that's bigger than a byte, how do you write it in memory? So the way that we saw was that you kind of like reverse it almost. So this is the least significant byte of the number, and this is the most significant. And the most significant is at a higher address in memory than the least significant. And if you're not familiar with the significance is basically like in a base system, how small the power of the base is. So like in base 10, if you have 123, it's like 1 times 10 to the second plus 2 times 10 to the first plus 3 times 10 to the 0. So the least significant digit in base 10 for 123 would be 3. The most significant is 1. So it's basically like, how big that part is. So little endian, you write the least significant first and the most significant last. Big endian is reversed. So you write the most significant first and the least significant last. Big endian would be like this. And so we kind of use big endian if you want to think about it that way, right? We write the most significant first and then go down in decreasing order of significance to the least. Little endian, most computers for optimization reasons use little endian, which is the inverse. Except now they're not really using digits, they're using bytes, or you could think of it as digits if you wanted to, base 256. So yeah, endianness, any questions on it so far? It's basically just kind of what order you write the bytes in. Nothing. I got a really smart crowd tonight. There are other kinds of endianness too, but Godspeed if you have to deal with something that isn't big endian or little endian. Very difficult. So we talked about memory. You kind of buy me that it's like a big array of bytes. Now we want to get into registers. So yeah, register, there are a lot of them in x86. Actually, let me stop for a minute. I keep saying x86. So every computer has like a processor in it, right? Does everyone buy that? I mean, there's maybe some weird situations where you might not, but every processor has an architecture or instruction set architecture that specifies what these machine code instructions are going to look like. What this is going to look like for certain code, and what this is going to look like for the assembly code. This is specified by what's called an instruction set architecture, which is specific to the processor that's in your computer. Fortunately, a lot of what you're going to reverse engineer is for Intel, because Intel is just like a cancer that's infected everything. Sorry, that was a little dark. But yeah, a lot of what you see is going to be Intel. So fortunately, you don't have to learn a lot of instruction set architectures. Another one that you might see in reverse or in capture the flag is ARM, because that's very common in the mobile world. But kind of similar to programming languages, if you know one instruction set architecture, it's kind of easy to understand another one. I'd say more so for assembly language than for programming languages because assembly languages are incredibly similar. So I talked about instruction set architectures. I talked about memory. But what the instruction set architecture does is it specifies the registers and what instructions you can run. So, sorry, registers. Let me explain what they are. Registers are these things that are inside the processor that can store values temporarily. So you might think of memory as a way to store something temporarily, and that's totally correct. There's also registers which store something temporarily, and you can think of them kind of like memory, except they're way faster than memory because they're actually on the processor. The other reason that we care about registers, despite being fast, is because most instructions that your processor is going to execute operate on registers rather than memory. So if you want to, add 5 to a number, typically what you do is you load that number into a register and then you run the instruction for add 5 to this register. So you can't even see this diagram because there's so many registers in it. x86 has a lot of specialized registers. The ones that you're kind of going to be interacting with the most are going to be like the general purpose registers. So these aren't all general purpose. So there's RIP and RSP kind of in the bottom right there. But the ones on the top are going to be the general purpose registers. And this diagram might look a little bit confusing if you don't know what it's trying to show you. So you see there's like a really big box for, actually, let me explain. So each of these like RAX, RBX, RCX, these like boxes are registers. And each register has a name. This is going to be how you address it from assembly. So maybe I'll go back to assembly so you can kind of see what that would look like. So if you remember, there was a register RAX. That was the name of it, right? It's actually not. RAX is not used in this code. But RBP, that's the name of a register. You can see like there's a lot of references to registers here. We'll go back to the registers. So RAX, register AX. But there's also boxes inside. I don't know if it's actually implemented that there's like a register inside of a register, but with x86, one thing you can do is you can address parts of a register. So first of all, I should probably clarify. I'm saying x86 a lot, but what I mean is x86 64. There's 2 Intel architectures that are not necessarily compatible. One is 32-bit, one is 64-bit. I'm going to be talking about the 64-bit version of that tonight. You might also know it as AMD 64 or x86 64. I might call it x86, and that's kind of incorrect, but that's what I'm going to be saying because it's kind of a force of habit at this point. But 64-bit, what 64-bit means, more or less, this can kind of be argued in a couple of ways, is the size of a register on that processor. So in x86 64, the general purpose registers are going to be 64 bits, or 8 bytes. And one of the things that you can do in x86 is refer to 4 bytes of that register. It's an 8-bit register, but you can refer to just the least 4 bytes and treat that as like a 4-byte register. And you would refer to that as EAX. So that's kind of the name for like the lowest 4 bytes of the register. There's AX, which is like the least 16 bytes. There's AL, which is the least byte. AH, which is the second most least significant byte of the register. There are reasons that you might want to address registers kind of partially. Maybe you're doing math on like ASCII characters, right? Like a char in C or Java is 1 byte, right? Is everyone familiar with that factoid? All right, so yeah. And if you're doing math on a char, you're probably going to be doing it in like AL as opposed to RAX. So yeah, register is kind of like a temporary place to store a value. Oh, yeah?
So like each of these little boxes is like an index to the register?
Yeah, you can think about it like that. It's so address, it's kind of like a way of saying like, hey, I want this part of the memory, right? So like these names are kind of like addresses, like you said. It's like saying I want this part of a register. So we have to disambiguate from memory and register. So we're going to use names instead of addresses.
And so you can record like the first 16 versus 15 bytes. Can you also recommend the second code to start with 15?
Unfortunately, you cannot. Yeah, you'd need a lot of names for that, and it's almost uncommon, right? Like you can't think of a lot of situations where you would want that part of the register, but you can get it anyway, right? Using some kind of math. So say I wanted the top 4 bits of RAX. What I could do is I could take RAX and, are you familiar with bitwise shifts? So I could shift that register 4 bytes down, and then now the least 4 bytes of the register are going to be what were originally the top 4 bytes. And then I can use like EAX to use that as 4 bytes. Make sense? Cool. Any other questions? None? All right, sweet. So we went over registers and memory. Now we're going to start to talk about instructions, and I'm going to introduce the most common instruction in x86, which is move, which is a bit of a misnomer because it's more like copy. Basically what it does is it moves or copies something from the source, which is on the right, to the destination, which is on the left. And that's, I've been using a lot of ambiguous terminology. That's also intentional because you can move from memory to registers, or you can move from registers to memory, or you can move from registers to registers. But what the syntax is, essentially, for writing to memory is you're going to have move followed by some keyword, and then the register. So, sorry, let me stop for a second. If you want to write something to memory in x86, you have to load the address into a register first. There might be cases where you don't have to do that, but in most cases, I think you do have to load it into a register. So you load the address into a register that you want to write to, and then you put the register name in brackets, and then you have a keyword, which I'll explain shortly. But followed by that, it's what you're going to be writing. So this is the number we were writing before, 0x dead beef. Each of these instructions write a number to memory, but each one is using a different keyword. And here's some kind of weird terminology, at least I think it's weird. Processors typically operate on words. So not word in the English sense, but word as in like the register size, which is weird. Because if you see the word keyword, we're using the AX, which you might recall is like the least 16 bytes. Weird historical thing. x86 came from like a processor series that was 16-bit registers, which is kind of why the word size is like 16 bits, but the registers are 64 bits. It's weird. But the bottom line is that the word for like a 64-bit value in x86 assembly is qword. Qword stands for quad word because 4 times 16 gets you to 64. If you want to refer to a 32-bit value, that's D word, as in double word, because 2 times 16. Word, 16, I just explained that, but there's also byte, which is 8-bit. So what the keyword is saying, essentially, is how big the value you're writing to the register. And there's actually an error in the slide because you can't have an address in AX or AL. That's too small. So pretend that RAX is in all of these. But the idea is I'm writing progressively smaller numbers. So this is a 32-bit value, but you could fit it into a 64-bit register, and you'd write it to the address in RAX. This is 32-bit, but you can't represent this number in 16 bits, so I'm going with a smaller number. Same case with the 222. That's something you can write in a byte. But the keyword over here is going to be corresponding to the size of the number that you're writing. And then here's how you would read from memory. It's kind of the same thing where you have the keyword, except you swap the order. So now does that sneeze? Okay. So now you have the keyword followed by the bracketed register on the right, and then your destination is going to be on the left. So this would go to the address in REX, read that keyword, so the 64-bit value, and put it into RBX, the register. And you can also move between registers. The semantics for that is kind of, I don't want to say obvious, because again, the move is kind of a misnomer, right? So what this is doing, it's not actually moving the value from RBX, it's just setting RCX to whatever's in RBX. So you can think of move as basically like set or copy, but in programming language semantics, you can kind of think of it as like almost setting a variable to something. So like you could say RCX equals RBX. That would be kind of like semantically equivalent to that last instruction. All right, everyone comfortable with move? Good, cool. So yeah, this is kind of coming back to the earlier slide on explaining what happens. Now you know what instructions are, you know what memory is, and you know what registers are. Now you should probably talk about RIP, because I put it here, and I just said that it's not a general purpose register. So this is a very special register. You can't actually use it as a regular register. Actually, you might be able to in x86, 64. In the original x86, it was kind of a pain. But sequential execution, right? Like that's good in some cases, but sometimes you want to do something more sophisticated, right? Like you might have an if case. Like you might have a program that like checks to see how many arguments you have. If you're not familiar with C, that's basically what this is doing. It's just saying like if the argument count is not 1, it should have been not 2. It'll do something different than if the argument count is 1. Now, can I zoom in on this? That's a real question. Maybe not. But 2 fingers. There we go. Sweet. All right, so here's the move we were talking about earlier. Now, here's our next instruction, which is kind of like the jump class of instructions. Basically, what a jump does is it sets RIP to something. So in our execution model, we're going sequentially. So we're running this instruction, then we're running this instruction, then we're running this instruction. But if we hit a jump, then it might set RIP to something else. So JE is one of the cases where it's not definite. It depends on kind of a condition. In this case, we're comparing. You don't have to worry about this too much, but this is basically saying if this value that's in a certain memory address is 1, then we're going to follow the jump. Otherwise, we're going to keep executing. So we're going to like go sequentially. But if this case is true, then we're going to stop doing sequentially and jump somewhere else. And that's kind of how you would implement if statements, right? Because like you can have the else case after that jump equals. So JE stands for jump if equals. And if it's not true, then you jump somewhere else, and you would jump to your if case. So then you have at the end unconditional jump, because if you're all right. So hold on, can I draw on the walls? All right. On the white wall. Yeah. I mean, not the wall, but not that bad. But you know, like you have the code for, and then because it's sequential, it's going to keep going into if not true. Yeah. I don't want to see this. My diagram was a little bit weak, right? We have 4 blocks, but we don't know where they are relative to each other in memory. This is kind of how they are. So the yellow block is going to be this one at the top. So we kind of always execute this because this is the beginning of the function. But we have this jump that checks to see if something's true. If it is true, then we're going to jump over here and then continue. So when we're done executing the if true block, we're going to fall through into that white block at the bottom with the leave and the rent. But if the condition's not true, then we're going to execute this. So this is like at the, sorry, I have this wrong. So the if true comes after. Yeah, sorry, I do have this right. So if the condition is true, then we jump down here. But if we're not, because we're executing sequentially, we go into this block because it executes sequentially, and these instructions come after the remember. But at the end, we have this JMP instruction. So that's unconditional jump. So the JE jumps if something's true. But if it's, you know, with JMP, it doesn't matter if any condition is true. It's just going to jump anywhere. So then we'll go here. And you can see the end goal is we always want to execute the code after. But we don't want to execute the true branch, right? Like if something's false, we don't want to execute the stuff that was inside the if. I was a bit worried about it. Does that kind of make sense? Any questions? Yeah.
For a sec. Switch your mask.
Oh, okay. All right, so that's kind of conditional jumps. Great. How do I zoom out now? 2 fingers? But I want to zoom in enough. Fancy technology. All right. Perfect. Thank you. All right, so we talked about kind of the sequential instructions, the move, how you get stuff in and out of memory through registers. We talked about basic control flow with the jumps. Now we're going to talk about the stack, which actually, is everyone here familiar with the stack? Yeah, but has everyone taken 187, or are you 121? Anyone not taken 187 yet? Oh, okay. Yeah, that's perfectly fine. So the idea behind a stack is it's kind of like a stack of pancakes, right? So the con-ops for a stack is you push stuff on top of the stack and you pop stuff off of the stack. You basically don't care what's below the top. When you pop, so push, you add a value to the stack, pop, you remove a value from the stack, but the order or the specific element that you're getting when you're pushing and popping is kind of in a specific way for a stack. So when you push something, it gets put wherever, but when you pop something, what you're getting in terms of the value is the value that was most recently pushed. Does that make sense? Yeah?
What's the function of the rest of the lower data set then, if you're just having it to kind of serve as almost a spring for the push pop?
Awesome question. So the idea is that you can push multiple times and then pop multiple times. So actually, I'll write it down. So let's say, all right, we're going to push 3 numbers. We're going to push 1. All right, so we push 1 first, then we push 2 second, then we push 3 third. So now the stack kind of consists of 3 values, so it's half of that diagram. And then if we pop a value, so we're going to say, okay, here's our stack. We want to pop a value off of it. This was the last one we pushed, right? So when we pop, it's going to give us 3. So we'll take this off of the stack. We popped 3. All right, we want to pop again. Now it's going to pop 2 because that was after 3, that was the most recently pushed, right? Right, so then we can push 4. So, all right, after popping those 2, we push on 4. What do you think happens when we pop?
We get 1.
No. So the top now is at 4 because before we push the 4,
Then we put 4 on.
yeah. So 4 gets pushed on top of the stack. So if we pop now, we get 4. Right. What happens if I push 5?
We get 5. There
Yeah. So we get 5 if we pop, then we pop again, and then we get 1. And now the stack's empty, so it's undefined behavior if we pop up. Yeah, what's up?
So it kind of works like a slinky. So like if you spring it up, it goes like this, just the opposite of whatever it's start. Like it work? Somewhat. Like does it work somewhat like a slinky?
I'll explain to you in the car.
Okay. I mean, I like the analogy. I'm just trying to think of how it would relate to a slinky. Because I put the slinky down the stairs and just kind of walked down. Yeah. But I mean, yeah. So I think I kind of get what you're saying, which is like the push and the pop are kind of like inverse directions almost. Like you grow upward, but you're removing downward. Right? Yeah. Make sense? Okay, sweet. So yeah, now we kind of want. Oh. Thank you. My tech support crew is unrivaled. All right, so that's how the stack works as a data structure. However, because we're computer scientists, we like to make things complicated. So in terms of assembly language, it's way more complicated. The stack that you're typically going to be dealing with in assembly is the call stack. So this might be familiar to you if you've written recursive functions in Java. Like, has anyone here written a bad recursive function and it just keeps on calling itself, and then you get a stack overflow? Yeah, so the stack overflow, that stack is this kind of stack, the call stack. What the call stack is for is kind of keeping track of the functions that are being called and for storing the information that's associated with that function. So that kind of, oh, do you have a question? No. Okay, yeah, no worries. So the call stack is consisting of, or the constituents of the call stack are stack frames, and each frame represents a function call. So the reason it's a stack is because you can have a function that calls a function that calls a function, right? So every time a function gets called, a frame gets pushed onto the stack. So the first call is like at the bottom, the next call is on top of that, and then the following call is on top of the whole stack. And then the inner function returns, so it pops it off of the stack. The middle function returns, so it pops that off the stack, and then the final, first function you called gets popped off the stack. So you can kind of see there's like an isomorphism between the order. But yeah, there's a lot of information on this diagram, and we're going to get into that. But the stuff that I want you to focus on right now is the stack pointer. So the stack pointer is basically, it's pointing into memory where the top of the stack frame is. In the kind of like conceptual operations of the stack, it's pointing to whatever's at the top, so it gets moved around as you push and pop. Frame pointer, don't worry about it, and the containers of the frames we'll talk about. But does the kind of stack pointer make sense? It's pointing to wherever the most recently pushed stack frame is. Anyone have any questions? The stack pointer is a register, so it's RSP. Maybe I'll go back to this diagram. RSP is the stack pointer, so this is the register that's always pointing at the top of the stack, unless you do something really weird, which happens. Yeah. All right, I'm going to throw you all a curveball. We talk about the stack growing upwards and you pop downwards. In x86, it's more complicated. For some reason, the stack starts at a high address, and as you push stuff onto it, the stack pointer goes down in memory. Does that terribly confuse anyone, or is it okay to just kind of like think about it upside down? All the diagrams are going to be growing upward, but you have to kind of think that like in practice, it's going to be going downward. Everyone good with that? Because we're going to look at assembly instructions, and you're going to kind of have to think about it that way. All right, I see no hands. All right, so some instructions that operate with the stack. You can use the x86 stack as a stack data structure. So there's like a push instruction and a pop instruction, which does exactly what I just explained up on the whiteboard. You can push a value onto the stack, and then you can pop it back into a register. And of course, like the size of the value that you're putting on the stack is like tied to the size of the register. So like push RAX pushes a 64-bit value onto the stack. You have to be kind of like coordinated with your push and your pop, because you don't want to like push the 64-bit value onto the stack and then pop off like an 8-bit value, or the stack's going to get misaligned and then it's bad. So do those two instructions make sense so far? Pretty much what we just explained, except now we're dealing with a memory and a stack pointer that points in memory. No questions? Okay. So what you're going to see a lot of are instructions that are manipulating stack frames, and there aren't really instructions that just do the whole stack frame thing. It's usually like a dance of a couple instructions. So the first thing you typically see in a function is like push RBP. So RBP is the frame pointer. I didn't really explain this as a special pointer because it's kind of acceptable to use RBP as like a general purpose register if you don't care about debugging your programs, but that's kind of beside the point. So the frame pointer is back here. It basically points to the beginning of the function's internal state. We'll kind of talk about local shortly and what comes after the frame pointer. But the idea is you push the frame pointer. I don't think it's actually in this diagram, but you could think of it as like right here. And then we move the stack pointer into the frame pointer. So now, actually, you could think of it right here. So we'll talk about the return address slowly, but shortly, but we'll push the frame pointer on here, and then we set the frame pointer to point here, right? Because we just pushed something on. So now the stack pointer is pointing here. We'll move the frame pointer to be here. And then the final thing we do is we move the stack pointer up, or in this case we move it down because this is a sub instruction. We didn't talk about that, but sub basically says, hey, I'm going to take this register and I'm going to subtract a value from it. And as I just explained, the stack in x86 actually grows downward, which is why we're doing a subtraction instead of an addition. So this, we pushed the frame pointer, we updated the frame pointer to point here, and then we subtract. And now it puts the stack pointer here. So you don't have to use push and pop to manipulate the stack pointer. You can kind of like disregard the fact that it's a stack and just move the stack pointer to wherever you want it to be. And that's what we do here. Does that part make sense? Okay, cool. You don't have to understand it super in depth. You just kind of have to understand that these three instructions are setting up the stack frame. And basically means, hey, this is the start of a function because that's what a function does to create a stack frame. When we're done, what we'll do is we'll use the frame pointer to get the stack pointer back to where it was at the beginning. We kind of saved the original stack pointer into the frame pointer. And then now, if you recall, the first thing we did was we pushed the frame pointer. So now that the stack pointer is pushing here because we moved the frame pointer into the stack pointer, now it's pointing here, we can pop the frame pointer and get the frame pointer to where it was before the functions because we're good citizens and we like to have our registers set to the values they were before we called the function. Everything good so far? Cool. All right. Last thing is going to be function calls. So how do arguments get passed to functions in assembly? A good way, as I kind of said at the beginning, is to just write some code, compile it, and disassemble it. And basically, in x86, you move the arguments into registers kind of in this increasing order. So EDI is like the first argument. As you can see, I called the numbers sequentially. So EDI is the first argument, ESI, EDX, so on, until you run out of registers for calling functions, and then you start pushing stuff onto the stack. That's kind of what we had here. So at the end of, or when you're calling the function, you push stuff onto the stack, / put stuff in registers. You kind of mix the two in x86. And then there's one more instruction that we're going to go over tonight. It's call. Does anyone want to take a gander at what that does? Not at the low level, like just kind of like high level, what does call do? Yeah, awesome. That's exactly the answer I was looking for. But at kind of a low level of how you call a function is basically the last part of this kind of dance with the stack frames. So when you call a function, you want to go back to the code after that function call, right? Kind of makes sense? The way you do that is you basically say, okay, I have the instruction of the, the address of the instruction that I want to execute after this function call, which is going to be whatever instruction is after call, and I'm going to push it onto the stack. That's where the return address comes from. So the return address is on the stack, and the inverse to call is ret, which is return, short for return. So what call does, it's basically like JMP, but there's an additional step where you push the next instruction onto the stack, or the address of the next instruction. And then what ret does is it just pops the address off of the stack into RIP. So then we're removing the return pointer from the stack, and then we go to that address. Make sense so far? All right, sweet. So this is what a function looks like in assembly. This hopefully looks familiar. We push the frame pointer, then we update the stack pointer, we update the frame pointer with the resultant stack pointer. There's no sub here because this function is really basic and we don't actually need a stack frame that stores anything. So then there's the code, and then the last two instructions are the end of the function, which is the closing of the stack frame. So you pop the frame pointer and then you return, which is, pull the return address off of the stack and then go there. All right, I labeled this as a mystery function. Does anyone want to explain or take a guess at what it does? I'll give you a hint. The IMUL instruction is kind of like the sub instruction, except instead of subtraction, it's multiplication. So it multiplies the register on the left by the register on the right. And another hint, EDI/RDI is the first argument.
Another hint, this function appeared
Oh, did it? Oh, well. If anyone was paying attention, then it should be an obvious answer. Squares it? Yeah, awesome. You're an assembly pro. You're ready to reverse engineer the world. All right. So yeah, quick summary, software reverse engineering. It's taking some executable artifact, determining a subset of its functionality, trying to figure out what it would be written like if you were the programmer. Executable artifacts are source code and go through transformation by compiler. And then we went over some basic assembly concepts and instructions. And now we get into the kind of fun part, which is learning how to use tools, because usually you're not going to be kind of dealing with the assembly. I mean, you might have to if you're reverse engineering something that's a little bit weird. But the tools make things a lot easier to reason about. And as I kind of described earlier in the talk, there's two methodologies for doing so. One is static analysis and one is dynamic analysis. I'm going to talk about static analysis right now. There are a good portion of static analysis tools. Some of them are very expensive. So IDA Pro and kind of the top left is like, I don't know, $1 million. No, not $1 million, but a couple $1,000s for a license. Binary Ninja is slightly more accessible. I think I saw a Binary Ninja sticker on Gilbert's laptop. Radari 2 in the bottom right is free, but very baroque and difficult to use. But what we're going to be learning about tonight is Ghidra, this cool dragon thing on the right. It's free. It's an internal NSA tool that was declassified like 2 years ago, written in Java, which I think is kind of to your benefit. I mean, I assume you're all fairly familiar with Java, which means you can write Ghidra plugins if you want to. Scripting is actually, sorry, did someone have a question? Okay, yeah, scripting, super useful in reverse engineering. You kind of want to automate a lot of stuff, so if you know how to interact with your tools, it's a good thing. There's also Python integration with JPython. But it's got a really good decompiler, and it supports like a ton of architectures. So I said that like you're mostly going to be reverse engineering x86 and maybe ARM. But you know, if you ever have to reverse engineer like 6502 or Hexagon, Ghidra's pretty good. All right, I didn't want to get into the slide. I want to actually show Ghidra, which unfortunately means whoever's watching the stream, you're going to be kind of in the dark for a moment. So let's go to, my laptop's dead. If it is, if it's not, I'm surprised. Okay, so minor intermission while I open up Ghidra.
Do you just want it zoomed in? Can you zoom in?
I think, so my terminal is going to be really small, and you probably don't care about what my terminal is doing. Oh, do you want me to pull up the QR so that people can download it? I was going to have that at the very end. I'm just kind of going, I mean, we're not going through the challenge right now.
Yeah, but if you want to download it, go ahead. Or go ahead.
Yeah, actually, how about I write the URL on the whiteboard?
What's
So,
the URL? I'll write it down.
okay.
Yeah, no, we'll write it.
You can pick any board.
I have great handwriting, I promise.
Okay.
This one at the bottom below the QR code.
Oh. Hold
I'll
on.
read it to you. Okay. I
So, yeah.
told you.
I'm going to be going over a program that's different from the challenge executable I wrote. Oh. All right, do you want me to dictate it?
Yeah.
Okay. Hotel.
Here.
No.
You said hotel.
I was using the. All right, I'll spell it. HTTPS. :// is.gd.
.gd.
Yeah. GD, like good without the O's. Oh, I used a URL shortener. You remember how I'm using like Discord to serve up the because I can't afford cloud hosting. Okay, //
Uppercase K.
lowercase k, uppercase k, 1 BD, lowercase b,
Lowercase b, uppercase L.
lowercase d. All right, uppercase M. All right, now you're good. Yeah, sorry for the ambiguities of.
Everyone! Woo!
All right, what do you want on the?
Okay, so my terminal is basically unreadable right now, but what's happening doesn't matter too much. I'm basically just opening Ghidra. If you're not weird like me, you're probably using like a desktop environment where you can actually click on a Ghidra icon and it like opens up Ghidra. But I'm sorry, I'm not a normal person. Actually, I might. Is there a way to zoom in on this, or should I try to see if I can make it bigger on here?
Probably just seeing them on.
Okay. So a couple seconds while I try to make the font larger. Okay, these are plugins, so it's probably not too much. Big deal. Ah.
Actually, should we just end the stream? Like, do you have more slides on?
I do have more slides, but yeah. All right, quick Google. How do you change the font size in Ghidra?
That's readable.
Is it?
Yeah, it says no active project. Or I'm looking at the wrong thing.
No, that's correct. I'm just trying to be respectful of.
Do you need the settings?
There's supposed to be an
Oh no, I don't.
project.
Whoops. All right, it's all right. All right, I just have to move this to a different workspace.
I don't know if that would help.
All right.
Yeah, the tip of the day is just.
Font.size.override. Let's give it a try. I should be able to do it pretty quickly. Font.size.override not recognized. Yeah. All right. Unfortunately, I think we're gonna have to stick with the tiny font. So I hope you all have 2020 vision. Oh, do you know how?
Should work editing this file.
Okay. So
Opt Ghidra support launch properties.
launch properties.
We're in the technical difficulty section of the show.
And there should be a
This is what happens when you
limits field
uninstall.
where you can set the scale from 1 to 2.
Wait, what's the issue?
Ghidra font size.
This is why you use an actual desktop.
You know, I have brought that up before,
Okay.
but no, he says no Windows so.
All right. Sweet. This is readable, right? Yeah. Thank you, Gilbert. All right. So yeah, when you open up Ghidra, it's really cute and it gives you a tip. Sometimes they're related to Ghidra, sometimes they're not. Let's see if I can find one. The largest diamond that was ever found was 3,106.75 carats. Did you know? Okay. Yeah, so you can disable that if you think it's annoying. I kind of like it. But yeah, when you open up Ghidra for the first time, basically what it's going to show you is like the project manager. So yeah, you have to create a project if you want to reverse engineer something. I mean, you don't necessarily have to. You can open up the tool specifically, but it helps to have a project. Basically maintains kind of like the correlation between different files because, as I said, you might have like libraries which are in different files than the executable you're reverse engineering. You can kind of import everything into a project and figure it out. Yeah, so projects, you create it. So like file, new project. There's like non-shared, shared projects. I would go with non-shared if you're not planning to share. You come up with a name. Does anyone want to give a, university appropriate name for this? Test. Cool. I like that. I like the way you think. So, yeah, it'll open up test. You get a folder. I've never seen this before. This must be new. Yeah, Geecher has a debugger now.
I think it's
That's-
just R2.
That's crazy. But yeah, so project, it's basically a folder, and you can kind of like import stuff as you need it. So in this case, because I have oops, I should have brought a mouse. So I'm gonna just like pick a random executable, maybe bzip too. You got like a dragon that's eating some bits and bytes, which I think is pretty cool. Alright, so it's a little bit big for my computer, but so when you do a batch import, this is what happens if you hit batch import. You can just import single files and it's less complicated, but I kind of fat fingered it. Let's see. Yeah, you hit OK, and it imports it, and all it does is it just like adds it to the folder. That's what importing files in Ghidra does. But you have to add a file to a project. It'll say, yeah, imported. Press OK. Cool. All right, now you have a file in your Ghidra project, and you can kind of open up the tools. But like at this point, the only tool I'm going to be showing you is the cool Dragon one, which is a code browser. So this is the disassembler decompiler. I think it's pretty cool that it pops up a Dragon. Maybe you don't. Makes me feel like I'm a cool NSA engineer. All right, yeah. So here's the program. Oops. Did I not open it right? Seemed to open an empty code browser, but maybe this would be better. All right, so yeah, cool. I got it to work. So you open up a file in code browser. And the first thing Ghidra asks you, very kindly, is this file has not been analyzed. Would you like to analyze it now? So analysis, basically, it's looking at all the metadata and all the code in the executable, and it's trying to decipher it into a way that would be, understandable to you. And it's customizable. So typically, you do want to analyze files you import. You might not if it's like a really huge file. I had issues opening up like the Team Fortress 2 code in Ghidra. It takes like a couple hours to analyze. Bzip 2 is pretty small. Why don't we analyze it? And then Ghidra is gonna, give you a list of analysis options, which I think is pretty cool. You can, you might only want like a subset of this, especially in the case of like those larger files that are going to take hours to analyze. I think for smaller files, the defaults are like pretty good. And I'll kind of go through a couple of these at least. So Ascii Strings. If you recall in the presentation, we used that strings command to like look through the file and find out stuff that was printable. That's basically what this does. It puts them in the Ghidra UI. Call convention ID. This is so I kind of explained how you call functions in assembly. It's not always that case. Sometimes compilers will use their own calling convention. This can identify them. Pretty useful. I would recommend not turning this on or not turning this off, although it is a little bit computationally intensive. Let's see. Demangler, that's a C++ thing. You'll definitely come across that at some point, but don't worry about it right now. Function ID. This is a really cool feature. I think it basically like looks at the code of a function, and if it looks like something it's seen before, it'll say like, oh yeah, this is printf or this is stir cat. Function start search. So this is looking for like the function frame start. The push RBP, move RSP, RBP. Stuff. That's what this is looking for, and it's basically going to identify all of the functions. It might not have the name for it, but it will at least tell you that, hey, this part of the code is a function, or at least I think it's a function. Yeah, stack. It's fun to look through. I think it's instructive if you kind of read the descriptions, but we're okay with that, with all of the default analysis options. So it's a bit hard to see, because the UI scale is so big, but we'll hit analyze. And this basically says, hey, I'm okay with all the analysis options, so go ahead. So yeah, here's code browser. This is the decompiler /disassembler. You can see if I scroll down, it's a little bit more sensical. Yeah, you see this? Move, call. You remember that? JMP, all the instructions we saw before. So right here is the disassembly listing. And on the right is the fun part, which is the decompiler. And you'll see it's working its magic, right? It looks like C. Amazing. Except these variable names make like absolutely no sense, like ivar1 underscore C. I had very specific parts about this tool that I wanted to talk about. But yeah, so this is kind of back to the thing I was saying about the decompiler not being perfect. Like it can't really figure out what these variable names is. So this kind of like just looks like gibberish. Doesn't make any sense. But there are some, this is back to the whole dynamic linking thing I said, where it's actually able to pull the name of the function that it's calling, even though it's in an external library. Strings, it's able to figure that out. But yeah, this is the decompilation, disassemblies on the left. This is most of what you're going to be looking at. But let's see. So on the left, you have some summaries of metadata in the executable. So symbols, you probably remember what I was saying. It's basically names for stuff that's in the file. And Ghidra is nice enough to collect those into different types. So you might have a symbol that corresponds to a class or an import or a function. Function's kind of most interesting if you're reverse engineering something in C. And these are basically the names of the symbols that it came up with. Some of these aren't actually symbols, but they're functions that Ghidra discovered using that find function analysis. And I don't think we can actually find main, which is a bit... entry? Yeah, entry might be our best bet. So in an ideal world, you'll be able to find main under the symbol tree. If the executable is stripped, however, what you'll find is entry. So this is what actually gets called first. It's not really main. But what entry does is it sets up for main. There's like this libc start main function that basically says, hey, here's main, go do this. So we'll go here. Cool thing about Ghidra is you can double click on function names and it will just bring you to the code. And yeah, so this is what main is apparently. Does that make sense? Let's see. Does it look like it's parsing arguments? Yeah. And I mean the top part kind of looks correct, right? Main returns an int. It takes a int and then maybe not a long, but char. And that's another cool thing about Ghidra is you can just like update the function signature as you find it. So we know that this is main. We know that param1 is argc. And we know that this is not a long, but it's instead a pointer to an array of chars. Okay, so we'll hit OK, and then we'll actually redo the analysis with this information that we added. So yeah, Ghidra can't figure out anything, but we're kind of smart, so we can figure stuff out and help Ghidra. And software reverse engineering is kind of like this collaborative symbiosis with your tools. Ghidra will tell you something, and you tell Ghidra something else, and then you kind of like work towards this shared understanding of what the program's doing. I think it's fun. It's like having a conversation with this like dragon on your computer. But yeah, you can see that it's like kind of making sense. Like you're, I don't know. This code doesn't make a whole lot of sense, but you're seeing like unzip, zcat. If you know how bzip2 works, it's actually like the same executable for multiple programs. It just has a different name, and it figures out what to do based on like what name you're calling it with. So I think this makes sense as main. But yeah, so that's the decompiler. That's kind of like the most important part about manipulating this is you're going to kind of figure out how like functions are called and stuff, and you're going to find out names for them, right? Because you're going to like figure out, as we did earlier, that this function is square, so we're going to give it a name and we're going to call it square so that the decompilation actually makes sense. Like it's adding square to square. Do you have a question? Okay, cool. Actually, at this point, does anyone have a question about Ghidra? This is kind of like the very high-level stuff that you first see when you open it up. Nothing? All right, cool. Bookmarks. You can set bookmarks Oh yeah, sorry, highlight. That's the other thing I wanted to show. So if you come across a variable like ivar15 and you want to see where else it's being used, you can middle click, which I don't think I can actually, oh I can. Okay, so yeah, if you middle click on a variable name, it'll like highlight it across the function so you can see where it's being used. This is useful because like usually you won't have a good name for it and you want to kind of like figure out how a variable is being used so you can name it. When you do come up with a name for it, you can right click and hit rename variable. I don't actually know what this is being used as, so I'm just going to call him Fred. You know, it updates the decompilation, but you know that's kind of the point of highlighting, is to kind of figure out where a certain variable is being used so you can give it a name. You can also highlight forward, so if you don't care about like use backwards, you can right click and highlight forward slash. There's a lot of options. Highlight's a kind of small feature, but it's useful. And now we're going to go into what you get from, window. All right, so if you need something that's not displayed right here, you click on window and it's got a bunch of options. Bookmarks is a pretty cool one. It makes it really small, but you can, so it bookmarks some automatic things like exit just through analysis, but if I want to like bookmark this address, I can just like right click and hit bookmark, and like it'll give it a name, or not a name, but a description and a category. You can come up with your own categories, you can come up with your own descriptions, random address. Comes up as a note, but yeah, it says like random address and bookmark. Hopefully you're not reverse engineering something so complicated that you need to use bookmarks, but you know, maybe you will. You can get the Bytes View. So this will kind of replace the decompiler, but you can swap between them. The Bytes View is basically like the hexadecimal I was showing at the beginning. It basically opens up the file and shows you the binary representation with the addresses updated to wherever the program would be loaded in memory. You might remember that I said that instructions are loaded into memory. So is the executable. It's just put somewhere in memory, and then the instruction pointer is kind of like reading through the code. Yeah, bytes, not quite as useful, but you know, maybe you're reverse engineering something kind of weird, and you need to know the exact structure of the executable file. The function call tree, this is pretty cool. So basically what this does is it uses the analysis machinery to say like what functions are calling this function and what is this function calling. So, you know, right now we're looking at fun 10 3, so maybe I'll go to main because we actually have a name for that. So let's see, main. Go back to main. All right, so there we go. So yeah, you remember that main gets called by entry, so the incoming references make sense, and then we can see all the functions that main's calling. Hopefully that makes sense to everyone. Whoops. Function graph. So this is kind of what whoops. Oh, my laptop died. Wonderful. Yeah, so I didn't have too much left to show. Basically, what the function graph is, it does kind of what I was showing in the earlier slide where there's an if. So there's like it basically breaks the function into blocks, and it has arrows going like based on what the jumping conditions would be. Ghidras are a little bit more readable than those like ASCII diagrams I had. If you go to window functions, it'll actually list like all of the functions in the executable, kind of similar to the symbol table thing, but this includes like functions that were defined through analysis. So I think those also show up in the symbol table, but at least the function list is kind of malleable, so you can like right-click, add files. So window/define strings, that's also a pretty useful one. So you can basically does what the strings command does, which is it looks through the executable file, lists all of the readable strings, and puts them into a table that you can read, and you can like double-click and find out where strings are being used. And yeah, that's Then the last feature of Ghidra that I was going to show is the cross-reference feature. This one, I guess I can kind of explain it through words. You basically right-click on like a string or a variable or a function, and you hit x-refs, x standing for cross, and it'll show you everywhere in the executable that function is called or that string is used. And that's kind of useful because say you're reverse engineering that software installer wizard that I was showing very early in the presentation. There are some strings that are showed in that wizard when you're doing the key verification, right? Let's see. All the way back at the beginning. So like there's product identification. Please type your 20-digit product identification number. So what you could do is you could go into Ghidra, you could hit window, define strings, you could look for one of those strings like product identification. You can find out where it is in the executable, right-click, cross-references, and then this string is probably being used from the function or some function that's calling the key verification algorithm. So this setup wizard might be like this huge executable with a ton of code that you don't care about, but the strings might lead you to the code that you do care about. That's kind of why xrefs and like define strings are useful. All right, so the ConOps demonstration got cut a little bit short, but are there any questions about Ghidra? Any questions? Yeah. I'm sure you'll have them when you're reverse engineering the challenge, but hopefully everything makes sense. A lot of the tools that you'll want are under window. They're fairly understandable. There is one more thing I wanted to say, which is the help tab. Ghidra has like a manual built into it that you can get to from the help tab. Super readable, super useful. If you have like any questions about using Ghidra, like that's kind of the place to go. You can search through it. Super useful. And yeah, that's Ghidra. It's primarily for static analysis, but as I'm finding out just now, it can also do dynamic analysis. It has a debugger built in. The debugger we're going to be talking about is GDB. So let's see. Fingers crossed that my laptop doesn't die again. Let's see. Can we swap it over? Yeah, we can probably go to the challenges. I don't think GDB is super important. You can look it up.
Do you still want to switch it?
No. So GDB is free, but you basically have commands to inspect registers, inspect memory as the program's running. You can set breakpoints, which basically means like when the function or when the computer gets to this address, we're going to stop and come back to the debugger, and then you can introspect. Should I put out like a follow-up document kind of explaining the basic ConOps of GDB? Yeah, I'll do that. There wasn't going to be like a whole lot to see, and you don't really need it for the challenge. One last thing I kind of want to talk about, if you can probably imagine that like software developers don't want people reverse engineering their stuff, like especially if it's a key verification algorithm. So that's where the reverse engineering category in Capture the Flag gets interesting. You have obfuscation, which is basically just transforming code in a way that preserves the execution semantics, so it does the exact same thing, but now when you disassemble it, it makes no sense. A pretty extreme example of this is this tool called like Obfuscator, which replaces every instruction with move. As you can see, like you have a pretty like sensical disassembly listing on the left. Then it turns into madness. The control flow graph looks pretty reasonable, and then on the right for Obfuscator, it's just like this straight line of instructions. So obviously, this isn't what the function's actually doing. The disassembler just doesn't know what's happening, so it displays it as like just a bunch of moves. So yeah, reverse engineering stuff from Obfuscator, not fun. Hopefully you don't have to deal with it. But that's kind of how you get around the whole static analysis thing. Like you just make the code harder to read or harder for the decompiler to parse. On the dynamic analysis part, which we didn't really get to, you're using a debugger typically, and anti-reversing measures for dynamic analysis are basically preventing debuggers from attaching to the program. So like in Windows, there's like an isDebugger present. Sometimes you can get through these by like patching out the call to isDebugger present or whatever the debugger checking function is. Sometimes it's a little bit more complicated. You can also just like use static analysis and forget dynamic analysis, but sometimes you can't do that. Basically, the point is, there are mechanisms for preventing reverse engineering that you might need to be aware of and get around if you're trying to reverse engineer something. Finally, there are analysis techniques besides static and dynamic analysis. So there's like symbolic execution, which is basically like analyzing the code and putting it into a parse tree, and then using some constraint solving to get to a certain program execution point. So I assume, actually, I won't go too much into this, but basically the idea is you put some like end condition on the program. So you might want to like say, oh, the end condition I want to get to is like accept the license key. And what the static analysis tool, or sorry, what the symbolic execution tool is going to do is it's going to parse the code, convert it into something that the symbolic execution can kind of like explore and figure out what inputs would get it to get closer to that state. And it's basically just going to churn through possible inputs until it gets to an input that gets you to the state that you want. So it's going to like just use constraint solving like SAT to get to the key. So yeah, that was a bit roundabout. Symbolic execution, we're not really going to be using it in this workshop, but it's cool to know about. This can get like really theoretical, but there's a tool called Anger, A-N-G-R, that might be worth looking into. It's pretty pragmatic. Like you can kind of just add an executable, say I wanted to execute this, and then we'll do exactly what I just said, figure out an input that gets it to that. And yeah, we're going to get into the challenge soon, but one thing I want to say, if you're going to go on and try to get better at reverse engineering, the best way to do it is just to reverse engineer stuff. So there are a ton of websites where they have just programs that you can reverse engineer and not feel like, you know, you're going to get arrested for it. So yeah, maybe I should say, like, don't reverse engineer the Windows license key verification algorithm. I think that should be kind of obvious, but, you know, don't do it. If you go to like reversing.kr, cracknews.one, they have like license key verification algorithms that were designed to be reverse engineered. I think they're fun. And then if you want a book, Reverse Engineering for Beginners is pretty good. It's like $1 by Denis Yurchev. Really long. It's kind of like a good reference material, but like you could also sit down and read it. It's not bad. It's pretty well written. It has a lot of domain-specific knowledge. So like what CRCs are, what function call tables are, stuff that you'll come across while reverse engineering that you might not have encountered while you're, you know, doing your programmer stuff. So kind of a good thing to have handy. It used to be free. You might still be able to get it for free. I don't know if I should say that. Yeah, so some websites and book. Yeah, challenge. So there's kind of two phases to the challenge. The first, actually, should I switch over and show it, or should I just let people? Okay, yeah. So if you run the program, it'll ask you for a password and an ID. So the easy part, figure out the password and hit OK. And it will tell you, like, yeah, the password was accepted, but the ID was not. That's the easy step. That should be pretty easy to figure out with Keydra. Actually, I take that back. There's a lot of like crap in that program. So part of the challenge was to get through the crap, to use like the strings and the xrefs to find out what you want to get to. But if you find it, it's pretty easy to reverse engineer. Harder would be to figure out the correct ID so that the password and the ID are correct, and then it'll tell you that, you know, your input was correct. And the URL to this file is on the whiteboard. So this is a tar.gz file. If you don't know how to open that up, you kind of have to be in Linux. You might be able to do it from Mac too, but the command is like tar xf followed by the and they'll give you some libraries plus, I think, a file called challenge, and that's the executable that you're going to be reverse engineering.
How much does this work?
All right. Now you get to reverse engineer stuff. I'll go around and answer questions if you have issues running Ghidra. Or you want me to check your solution?
Well, I guess I'll stop the stream.
Okay, cool. Should I take this off too?
Oh, yeah.